Hey folks, I'm continuing the homework questions from Tuesday, March 23rd, and we're just going to do the last few questions on this second video. So this is page 146, number 11, and we have a cylindrical shaped tin can that has to have a capacity of 1,000 centimeters cubed. Assume the dimensions that require the minimum amount of tin, or determine the dimensions that require the minimum amount of tin for the can, assuming no waste. So here, again, you always first want to identify what are you going to try to minimize or maximize. What am I doing the derivative of? What am I trying to optimize? So that's the surface area, and the surface area of a tin can or a cylinder is 2 pi r squared, which is the top and bottom, plus 2 pi RH, which is like the around the sides part. So we are also given some restrictions that the diameter is going to be 6 and the height has to be at least 4. So let's figure out what other information we know to get this into one variable, because the fact that I have an R and an H, that's problematic. I need to figure out what this would be in terms of just one variable. I think I'm going to try and get rid of that H because I feel like the H is an easier thing to sub into rather than the R squared and the R both in there. The other information I know is that the volume of this is 1,000 centimeters cubed. So I know the volume of a cylinder is pi r squared h. So if that's equal to 1,000, then h is going to be 1,000 over pi r to the negative 2. And I'm just going to putting this negative exponent because I know I'm going to need that when I do my derivative. I could just put 1,000 over pi r squared, though that would be fine as well. So I'm going to take this and sub it into my surface area equation for H, and then we will look at the boundary conditions. So here I've got surface area 2 pi r squared plus 2 pi r times 1,000 over pi r to the negative 2. So when I clean this up a little bit, that pi on the bottom will cancel out, which is really nice. And then here I'll have 2 pi r squared plus 2,000 r to the negative 1. Because when I add those exponents, the 1 and the negative 2 would be negative 1. And then, not surface area anymore, I'm doing the derivative of area with respect to the change in radius. So taking the derivative here is 4 pi r minus 2,000 r to the negative 2. And we want to find where the derivative would equal 0. So that would be 2,000 over r squared is 4 pi r. So 4 pi r cubed, so 500 over pi is r cubed, so r is going to be the cubed root of 500 over pi, and I think we are reasonable, especially with a word problem, to just figure that out to a couple decimal places. So the cubed root of 500 over pi is about 5.42 centimeters. Now, I am given information here about this relationship. So I know that the smallest diameter is 6, but that's not what I'm actually measuring. I'm measuring a radius. So we have to adjust that and say, what's my restrictions on my radius? The smallest radius would be 3 if the smallest diameter is 6. And what would the biggest radius be? we could figure out what the biggest radius would be by putting in a height of 4. Because if the height is as short as possible, the radius would have to be big to make up for that. So if I say 4 equals 1,000 over, well, maybe going back to the original might be easier. So 1,000 equals pi r squared times 4. So 250 over pi is r squared. Then the biggest radius, 250 divided by pi, and then square root that. The biggest radius I could have would be about 8.92. So I don't have to analyze the signs of the derivative here at all because I do have these endpoints. You should always double check that the value you get where the derivative is 0 is within this interval. Sometimes it's not. And then you would say, well, there might be that turning point or that minimum, but it's outside the bounds of what I've been given for the question. So then we're just going to check. What's the surface area? Like the area if the radius is 3, the area if the radius is 5.42, and the area if the radius is 8.92. We're just going to put that all into your calculator and calculate what it would be. So I've added those numbers in, and as you can see, the minimum surface area happens at that 5.42 for the radius. So therefore, the minimum amount of tin is a radius of 5.42 centimeters. And we could figure out if it asks for the height there. Of course, you could just sub that in and find the height. Okay. The next one, I had kind of a good question here about how to set these up. So I'm going to look at the setup of number 10 and number 12 both. I'm going to start with number 12 because somebody asked that kind of specifically. So here, determine the area of the largest rectangle that can be inscribed in a right triangle if the legs adjacent to the right angle are 5 centimeters and 12 centimeters long. The two sides of the rectangle lie along the legs. So what we have is a right angle triangle with sides of 5 and 12, and we want to fit the biggest rectangle in here that we can, maximum area that we can fit in there. So maybe we want to put it really high up on the 12. Maybe we want to put it like half and half. We don't know really like what shape, but you're going to build this rectangle and you're going to fit it into that right triangle against two of the sides. We need to have some kind of variables here. And there's a few different ways of looking at this in terms of the setup. I'm going to call this X and Y just because, so let X be the width, let Y be the length. So there's different ways of doing that. I could have done W and L, but I see this kind of set up on, we want to figure out a relationship between our X and Y, and I see this as sort of something that I would picture being on a Cartesian plane. So I personally like the X and Y, but there's other ways to do this as well. So what we would know is that we are trying to find the area of the largest rectangle. So we want to maximize area. So we know here that area is x times y. It's a rectangle, length times width. So now the tricky part here is figuring out what's a relationship between this x and y where we would have something to sub in and eliminate one of those variables over there. So there's two good, very different solutions of how I would see this. And I alluded a little bit to the first one, that I personally look at this right away. I kind of think, hey, like that looks like the XY plane to me. And I want to really figure out that point there. Like what point is that going to touch that kind of diagonal slanted line? And that's really just how I drew it. It's a little bit arbitrary to put that on there. But I would know that if I put this on the plane, that this line, we can find the equation of that. That's going to be y equals, and think about what we need for the equation of a line. We need a slope, so a rise over run, negative 12 over 5, x plus the y-intercept, which is 12. So that's, to me, looking at that, I say, oh, okay, I can find the equation of that line, and then I know that I can find any y value sliding along that diagonal for the given x value. So if I know the x value, I can figure out the y value. So that is how I would do this question, and I would sub that in. So I'd have x and then negative 12 over 5x plus 12, and then just work this out and find where that area would be a maximum. So negative 12 over 5x squared plus 12x, and I can restrict x in here to the interval 0 and 5. And it's kind of arbitrary that I picked x being along the length of 5. That could switch easily. So I would do the derivative here. A prime is negative 24 over 5x plus 12. And where does that equal 0? So 24 over 5x equals 12. X equals 60 over 24. So x is 2.5. Which is halfway across there. So then I would check what is the area. I'm gonna do this actually over here. So I would check the area if x was 0, which is not good. That's gonna be 0. And the area if x is 5, also not good. That's 0, but the area if x is 2.5, we can figure that out. 2.5 squared times negative 12 over 5 plus 12 times 2.5. So that would give me an area of 15, and these are centimeters squared. So obviously that is my maximum. I do want to show a different way of looking at this. If you hadn't visualized this like as on the Cartesian plane. So if you had another way that people have gotten really good at looking at these, I'm going to draw this on this bottom one here. If that's my x and that's my y, is by looking at similar triangles of those two triangles. So if we kind of take a look at these two similar triangles, that would be x, and this side would be 12 minus y. And this little triangle at the base, that would be y, and this would be 5 minus x. And we know that the relationship of similar triangles is that the ratios of those sides are equal. So we could say 12 minus y over x equals y over 5 minus x. And if we cross multiplied here, we can figure out an equation for x or y, an equation for x or y in terms of the other one to sub back in there. So this is another way to set that up that does work out really, really nicely. And you would be able to go through and solve for that. The question number 10, let me just take a look at that one because I do want to address like the setup of it. If I can find a little bit of space here to draw that in. I am kind of full in here. Number 10 is, I'm just going to delete this if I can. If I do a little bit of the setup for number 10, this says the largest rectangle that can be inscribed inside of a semicircle of radius 10 units. So we have a semicircle like this, and we want to put the biggest rectangle possible inside of that semicircle. And this one, I would very much recommend, again, putting this like on the Cartesian plane like that, so that that's the x, y. And then we would know that this point would have a hypotenuse of 10, and we would have an x and a y, where x squared plus y squared is 10, and the area of this whole thing is the length, which is 2x times the y, because we would have like double, it would go in both directions. That's how I would set that one up. And then you'll use that Pythagorean theorem of that right angle triangle to sub in for one of the variables, x or y. Then number 13, if we take a look here, just pull this down, we have an isosceles trapezoid. So that means it's symmetric on both sides. And it's going to be made so that the angles at A and B, so here and here, are going to be 120 degrees. This sheet metal is 5 meters long, but that's actually kind of irrelevant until we want to figure out the volume. But what we want to do is figure out what the cross-section area will be maximized. So like that trapezoid, we want that to have a maximum area. And we know that these are going to be 120, and we have 60 centimeters total to go from DA to AB to BC. So we want to really maximize that if we're given this 120 degrees. So let's try and sketch that out. Just scoot that up. And I don't know why, but I always draw my trapezoids like I don't like them with the big side at the top, even though this is a little bit upside down. So we know that that is 120 degrees. And we know that the area is going to equal the A plus B times H over 2. That's the area of a trapezoid. So A and B are the top and bottom. H is the perpendicular height. So we need to figure out what would maximize this area. So here we know that the 3 sides added up will have to equal, let's say, x, y, and y. So x plus 2y will equal 60. Now I have to figure out a, b, and h all in terms of x or y. So a, b, and h. That's what I'm going to be looking at. So I know if I kind of drop a horizontal here, and this is 120 degrees there, that would be left with 30, and that is 60. Just because of that 90-degree angle up and down, I would have 30 left over from the 120 and a 60 at the base there. So if I wanted to figure out the height here, this height over y is equal to sine 60. So I would say h over y equals sine 60. So h equals y sine 60. Okay, so we know that sine 60 is root 3 over 2. So this is going to be root 3 over 2 times y for the height. The top is easy. The top is just my x. Now, the bottom is going to be harder. The bottom is going to be harder because I need to have this x in the middle, but I also need to figure out that distance there. So I'm going to call that, running out of letters there, I'm going to call that maybe z there and there. And then I'll have an x here. So b is going to be x plus 2 z's, and I have to figure out using my trig what that z measurement would be. So I would know that z over y is cos 60. So z equals y cos 60, and cos 60 is 1/2. So 1/2 y. So x plus 2 times 1/2 y, and then that would just be x plus y. So I have the 3 pieces of this area equation in terms of x and y. I don't really want them just in terms of x and y. I really want them just in terms of 1. So I think it's easier to solve for x, so I'll call that 60 minus 2y, and sub that in wherever I have a y, an x, pardon me. So a is going to be 60 minus 2y, b is going to be 60 minus 2y plus y, so just 60 minus y. And then h is going to be just root 3 over 2y. That's already set. And I think I am going to very likely run out of space here. But I would put each of those in, and then we're going to do the derivative and solve this for where the derivative would equal 0. So we are going to end up, I took way too much space here. We're going to be super squeezed. So a is 60 minus 2y plus 60 minus y times the height, which is root 3 over 2y, over 2. So the area is going to be, I won't have space to finish this, but 120 minus 3y, root 3 over 2y over 2. But it ends up being not a bad derivative at all. It's just going to be quadratic. That root 3 is a little bit of a mess, but it's going to be totally manageable. So here I'm going to multiply this root 3 over 2 times the 120, which would be 60 root 3, but then divide by that 2 on the bottom. So I'm going to have 30 root 3y minus, and now multiplying this in with this 3, so it'll be minus 3 root 3 over 2 here, and then that other over 2 will be over 4. So 3 root 3 over 4y squared. So the derivative of the area is going to be 30 root 3 minus 6 root 3 over 2y. And this is pretty straightforward and easy to solve that for y, even though I'm a little bit out of room. The one thing I do want to do is look at what the restrictions would be. If I have a total of 60 centimeters for x and 2 y's, then I would say that y, the restrictions on it, its smallest could be 0, which is a terrible idea, but not impossible to do. You wouldn't have a very good area there. The biggest y would be 30 if you had half there and didn't have a bottom at all. If you squished in that base of the trapezoid so small that it would be a triangle. So I would check a prime equals 0, solve for y, and then you're going to check 0, 30, and the result you get when you solve for y there. Just go to 2 decimal places. Okay, the last homework question here. A train leaves the station at 10 a.m. and travels due south at a speed of 60 kilometers per hour. Another train has been heading due west at 45 kilometers per hour and reaches the same station at 11 a.m. At what time were the 2 trains closest together? So let's draw this out. We'll draw our little like north, south, east, west. There's the station at the start, at the center. So at 10 a.m., we know that the first train is at the station and it goes south at a rate of 60 kilometers per hour. So train A, I'm going to call this A. That distance is that the train has gone. So train A is, let's say that would be 60t. And I'm going to say let t be time since 10 o'clock. Okay. Now, train B, it starts over here. Whoops, no, it does not. It's going to the west. It starts over here, and it's moving west at 45 kilometers per hour. Now, if it gets to the station at exactly 11, then it started 45 kilometers away because it took 1 hour to get to the station. And this distance B is going to be decreasing every amount of time that passes. So the distance B will be 45, that's what it starts at, minus 45t. So after 1 hour, it will be at a distance of 0. It will be at the station. So I'm going to set up a shape, a triangle, to measure the distance between them. So this would be A, and that's B, and that's D. So I know that the distance squared is A squared plus B squared, or that the distance would be A squared plus B squared to the exponent 1/2 if I wanted to find the derivative of the distance. And I want to get that distance in terms of time. So I'm going to say D at T. So I'm going to sub in what I know about their times, and I want to put restrictions on time. So we don't know what was happening before 10 o'clock. So I'm going to say T could be 0, like exactly at 10 o'clock, or T could be let's say 1 hour, because they're getting farther away. I think it's reasonable to restrict that to 1 hour. Because at 1 hour, this train A will be 60 kilometers south and train B will be there. They're quite obviously shorter distance than that right at the start. So that distance would just be growing if they were going out from there. Okay, so from here, we're going to take each of those values and sub into our function. So here we know that A is going to be 60t, and that's squared, plus B, which is 45 minus 45t, also squared, all to the exponent 1/2. I definitely want to clean this up and simplify in those brackets before I do the derivative. So this will be 3600t squared plus 2025 minus 4050t plus 2025t squared, all to the exponent 1/2. And again, clean this up a little bit. So here I've got 5625t squared minus 4050t plus 2025 to the exponent 1/2. Then when we do our derivative, we'd have 1/2, and just kind of to save space, I'm just going to leave this bracket. You should not do this on a test ever, but I can't make another Jamboard because I'm at the 20th slide here, and I will run out of room. So I'm just not writing that because it's going to go on the bottom. And then times the derivative of the exponent, which is 11,250t minus 4050. And if we want d prime at t to equal 0, then that would be, so this would be 11,250t minus 4050 over 2 root that thing that I can't fit. That's going to go in there, or to the exponent 1/2. So what I'm really looking for, if this equals 0, is if the numerator equals 0. If the derivative equals 0, then 11,250t will equal 4,050. So t would be approximately actually 0.36. So that's an exact value. We want to figure out what that is in minutes. So it's 0.36 hours. I'm going to do times 60 to get the number of minutes. So 21.6 minutes. So closest at 10:21. I guess 0.6, you could figure out how many seconds that was, and 36 seconds if we wanted to be that detailed, but to the nearest minute, I think that that's reasonable.